Okay, I'm eating my lunch while I do this. Problem 2 I'm going to do is 648, and it is the mass pulling another mass on a frictionless surface. Oops. And they ask you to calculate the acceleration of the system. These two blocks will have the same acceleration. Again, the tension in the rope is going to be the same throughout. So these same two accelerations are the same, and the tension in the rope is the same because we're going to assume the pulley is massless and frictionless. The first part of this, all you're given are the masses of the two objects, and the first part of this asks, is the tension, the strength, greater than, less than, or equal to the weight of the hanging mass? Well, you know if this is accelerating downward, you've got an unbalanced force in that direction. So the force diagram must have a downward force, which is the earth on the block, that's greater than the tension going up. So you can see that the tension has to be less than the force of the earth on the block to be accelerating downward. So that's a pretty easy question to answer right there. It's kind of like being in an elevator, and when the elevator accelerates downward, you are actually feeling lighter than normal. The second part asks for the acceleration of the blocks. To solve that, we have to draw force diagrams of each one of these separately. I'm going to call that one M2, I'm going to call this one M1, and that second one that's hanging M2. So we're going to remember the tension is the same in both places. We remember that the acceleration of this block is equal to the acceleration of that block, and we're going to proceed with that information that will allow us to relate the motion of those two to each other because of those constant variables. So let's start with the hanging block, which is M2 in my diagram. This is the force of the earth on block 2. It's equal to M2 times 10 newtons per kilogram. I'm going to use the symbol G. The tension force up is less than that. I don't know what that is, but I know I'm accelerating in the downward direction, so that has to be shorter than M2G. The force diagram for M1 is going to have the force of the earth on this block, which is going to be equal to M1 times G. And then the normal force going up, which is equal, because I'm on a flat surface and no other forces with Y components pushing down or pulling up, that's going to be, I'll just call it the force of the table on the block. We're not going to need to use that at all because our unbalanced force, since there's no friction here, it's a smooth table. Let's go back to that. They say here, smooth tabletop, that's code for frictionless. That's how I know there's no friction on that. Okay? So there's no opposing force here. My tension is unbalanced, and my tension is the unbalanced force equals M2 times A. So I'm just using my formula, F unbalanced equals MA. The only unbalanced force that exists here is tension. So tension is equal to M2 in this case times A. I actually didn't write my formula over here. The unbalanced force equals M, oh shoot, this is M1. Sorry about that, guys. Sorry to be so confusing. That's M1A. This is M2 over here. So the unbalanced force equals MA. The unbalanced force in this case is M2G minus the tension equals M2A. So this is the MA part of the equation. This is the unbalanced force part of the equation over here. The difference between these two, M2G and T, is my unbalanced force. And it's equal to the mass times the acceleration of that block. The common variable here is T. So what I'm going to do is I'm going to substitute M1A in for T. So M2G minus M1A equals M2A. Okay? Now I'm going to get all my A terms on one side and solve for A. So that just means M2G equals M2A plus M1A. Factor out my A. M2 plus M1. And then divide. Now you might wonder why I have not substituted in any numbers here, and I'll tell you it's because we can learn a lot from this equation right here as it's written for acceleration. because this is called a modified Atwood's machine. The system is both blocks put together with the rope. If you notice, the force that's accelerating the system is that block right there is doing all the work, okay? So this is actually the net force of the system right here in the numerator. So this is like the net force of the whole system is the mass of block 2 times g is the net force on it. It's by itself trying to accelerate those two masses together. That's the mass of the system, m1 plus m2. So this is like the system mass. So that's the net force on the system. This is the system mass. So in our problem, we have M2 is 2.8. I'm going to use 9.81 because it seems like we get a slightly rounded off wrong answer when we use 10. And the sum of those two is 3.5 plus 2.8. And that's my acceleration. So putting that into my calculator, I'm going to get in the numerator a net force provided by the weight of block 2 of 27.5 newtons, and I get the system mass is 6.3, so I get an acceleration of 27.5 divided by 6.83. We would certainly expect it to be less than the acceleration due to gravity, because if this thing was in free fall, if mass 2 was in free fall, then its maximum acceleration is going to be 9.81. If these two masses were, or if I should say, if mass 1 was really, really, really big, it would be a very small acceleration. Notice this equation again. By the way, here's my answer. I'll type in just a minute. I want to show you a little insight here. Is that as m1 goes to 0, so that's the mass on the table, as that gets smaller and smaller and smaller, the acceleration over here on this side gets closer to g, 9.81 meters per second per second. I can cancel out the two m2s if m1 is 0. So if the mass of this block on the table goes to 0, that equation shows us that's going to go into free fall. Conversely, if mass 1 gets really, really, really big, if this mass gets really, really big, that's in the denominator added to mass 2, my acceleration gets smaller and smaller and smaller. That makes sense too. Okay? Let's go back and type in our answer here, 4.03, and see how we did. They probably wanted 2 sig figs, I'm guessing. I'm going to give it 3 anyway. Like it. No, that's not so cool. Let's see what we did wrong here. 27.5 divided by 6.3, it looks like that's correct. Let's see if I can troubleshoot this real quick. Okay, you might have caught this careless mistake when I was going fast here. 4.36, I just did my math wrong on the calculator. So I come back, hopefully that works in my formula here, 4.36. We're about to find out why this is so exciting. It's exciting when you stay on the same page, I guess. There we go, okay? Tension in the string is pretty easy now that you've got that. All you have to do to find the tension in the string is come back to, sorry about that, come back to either one of your formulas. Probably this is the easiest one. Substitute in mass 1, which was 3.5 times my acceleration of 4.36, and we'll get the tension in the rope. 15.3 newtons. Let's see how that works. Okay. All right, I'll do one more problem, the last one on a separate screencast. Hopefully that helps you.